In this video, we take a look here at chapter 2.6, linear regression. So we are going to see how to use matrices to find the line of best fit. All right, so the idea of linear regression is when you have a set of data points, you want to make a model to fit it. So right now we're going to look at linear regression. We will see you can also do polynomials of best fit, or exponential models of best fit, or logarithm models of best fit, etc. So any algebraic model can be a model of best fit. So here in the first graph, we've got our set of 5 data points and 2 contenders for what we call the line of best fit. So the line at the steeper angle is y equals 1.2x, and the line at the less steep angle, the lighter gray line, is y equals 0.5 plus x. So both lines are pretty good matches for the data points. We want to figure out, well, how can we analyze which line is the line of best fit? So over here on the right side of the screen, I have 2 graphs. The first graph, model 1, corresponds with y equals 0.5 plus x. And we can see in this model how far is each point on the line for the corresponding x values from the actual data point. We call this the error. So you can see when x is 1 here, we have a value on the line is above, so the line's an over predictor. And we find the error is the actual value minus predicted value. So this would be a negative error because the actual value is below the line. When x is 2, here's our error. It's also, the line is over predicting, so the error would be negative because the actual value is below the prediction. And then when x is 3, we're getting an over prediction. When x is 4, we have an under prediction. And when x is 5, we have an over prediction. Now you can imagine it might be problematic if we just add up the errors, because if they're positive and negative, they might cancel each other out and not give us a sense of the true amount of error. So as statisticians, we have a few different ways that we can think about the total error without having the negatives cancel out with the positives. So one way is to use the absolute value. That's called the absolute error, and it is a calculation that we do in the field of statistics. The more commonly used method is to square the errors. We know squaring values make small positive, so we're going to look at that approach in this example, and that's what's most commonly used by statisticians. The one reason that squaring is more commonly used is because think about computers and runtime. If you ask a computer to do an absolute value calculation, it has to check the value and then see what it is. You know, is it positive or negative, and then convert it to being positive if it's a negative value. Whereas if you are squaring numbers, you're just multiplying. And so usually multiplication has a faster runtime in terms of computational time. So that's one reason statisticians prefer to use the squares instead of the absolute values. All right, let's take a look at model 2. This is y equals 1.2x. So we see the first point is pretty close to the line. When x is 2, it's a negative error. The line over predicts. When x is 3, the line under predicts, so it's a positive error. When x is 4, the line over predicts, so it's a negative error. And when x is 5, it looks like we're right on the line. So it's kind of hard to eyeball, but overall, it looks to me like model 2 is actually the line of best fit because we've got less overall error there. So the line with the least error is what we call the line of best fit. And you'll learn it actually doesn't matter if you do the absolute values or the squares. Either way, when you tally up the error, you get the same best result for whichever line is the line of best fit. So we, in this table, square the differences between the line and the data point to create a measure of error. That's called the sum of the squared error. So each row here corresponds to one of the points. And then here is f of xi is the value from the line of best fit. So you can see the points are all the same in both sides of the table. And then our f of x's, our values from the 2 different models, are slightly different. And so we get the errors here. So we see, oh yeah, 1 minus 1.5 gives us this negative 0.5, and then we square that In model 2, 1 minus 1.2 gives us negative 0.2, and then we square that. And then we add up all of these square errors and compare the sums. So comparing the sums of the squared errors, our winner here is model 2. That is the model with the least error. And so you might say, well, gosh, we could spend all day here trying to come up with different models to figure out which is the line of least error or the line of best fit. So we actually have a process that we can go through with matrices to figure out algebraically, well, what is the model with the least error? So let's take a look at that process. So of all possible linear models for a given set of points, the model that has the best fit is a linear model that minimizes the sum of the squared error. And this model is what we call the least squares regression line. So here's the definition. So for a set of points, x1, y1, all the way through xn, yn, we're doing this in 2 dimensions. Know that it's essentially the same process if you've got x, y, z in 3 dimensions or up to n dimensions. So for our set of points, and the least squared regression line is the linear function f of x equals some constant, we'll call it a naught, plus coefficient a1 times x. That minimizes the sum of the squared errors. So each of these squared errors are the actual value minus the predicted value, and then it gets squared. So just know we always do actual minus predicted when we do the subtraction. Although if you're squaring or absolute valuing, it's not going to make a difference if you forget and do the opposite. Okay, so to find the least squares regression line for a set of points, begin by forming the system of linear equations for each one of the points. So if we've got n points, we can form equations y1 through yn, where each entry, for example, y1 equals the function evaluated at our x value, and then we add to that the error, y1 minus f of x1 here. And we do that for all of the equations. Does that make some sense? So you take your prediction and you add the error, and you're going to get back your actual value. So let's write that out a little bit. So it's actual value equals prediction plus error. We call our error epsilon usually, or an e, I think a little lower. And that makes sense because we know the error is actual value minus prediction, or observed minus prediction, we sometimes say in statistics. All right. And then, so we're saying this right-hand term right here, whatever the y value is minus the corresponding prediction of each equation is the error in the approximation, where we're trying to approximate the actual value yi by the predicted value, the function evaluated at xi. So if we go back to our picture, okay, this value here is our that's our actual value. So our actual yi is 4 here, and our predicted value here, f of xi, is 5. Does that make sense? Our predicted value is on the line. So you see, okay, our error then 4 minus 5 is that -1 that we saw. And that was, where was that? Oh, I guess it was a 4.8, but it was right here in the table. So what I called 5 is actually 4.8, but close enough. All right, so we call this error, sometimes we use this epsilon I used, or we use E sub I. So each error is the actual value minus prediction. So we can rewrite our equations from the top line as each y value equals its prediction from the linear line of best fit plus the errors. So this right here is just what we were calling the function, the line of best fit function at x1. All right, so now we're going to think about defining these values as matrices. So if you head back here, each y value can be put into a column matrix. And then think about what the coefficient matrix would look like for all of our a naught plus a1 x1 values, or a naught plus x1 a2, right? The coefficients here are going to be a naught and x1. So we create a coefficient column matrix here, A equals A naught A1, and that's going to get multiplied by our x values, where since A naught is a constant, we'll just say, oh, our x value can be 1. And then for A1, our x value is going to be x1 through xn. And then our errors are in the matrix E. So then we can think about the n linear equations represented as these matrices. Our system of linear equations is a matrix. And so that equation is y equals xa plus e. So note that the matrix X has a column of 1s. That corresponds to the a naughts here, because a naught times 1 will just give us a naught value. And then the xi's correspond to the a1 coefficient multiplied by each x value. That's the slope times x part of the linear equation. And this matrix can be used to determine the coefficients of the least squares regression line, as we're going to see on the next page. So for the regression model y equals xa plus e, the coefficients of the least squares regression line are given by the matrix equation A equals, and then we work backwards to see, oh, x transpose x inverse times x transpose y, where the sum of squared errors is E transpose E. So this is how we find the coefficient of the least squares regression line. And we'll see this again later on in the semester in chapter 5. And then if you take a upper division statistics class, you actually get to do the proof of this to find the coefficient matrix. So let's take a look at an example from wildlife. So a wildlife management team studied the reproduction rates of deer in 3 tracts of a wildlife preserve. The team recorded the number of females X in each tract and the percent of females Y in each tract that had offspring the following year. The table shows results. So we've got 3 data points here. We'll list those as 175, 120, 68, and 140, 55. And we are going to find the linear regression model, or the line of best fit, using matrices, of course. All right, so if we go back to our equations, remember our X matrix is going to be all 1s in the first column and then X values in the second. So we actually have our X values here. That's 100, 120, 140. So we can say here our X matrix equals 111 and 100, 120, 140. And then our Y values will correspond to the Y matrix. So the Y matrix will be 75, 68, 55. And then we next in the equation want to calculate X transpose X for this part of the equation right here. So X transpose X is going to be 111 on the top row, and 100, 120, and 140 on the bottom row, multiplied by 100, 120, and 140. Okay, and you can do this either in Simpy or by hand and see, all right, that first value is going to give us a 3 because you got 1 plus 1 plus 1. Does everybody see we're going to get a 2 by 2 matrix? Because this is a 2 by 3 matrix multiplied by a 3 by 2 matrix. our next calculation is all the ones multiplied by the 100, 120, 140 summed up. So that is 360 here. And then by symmetry, we get the same calculation, 360. And then the 100 times itself, 120 times itself, and 140 times itself added up give us 44,000. All right, our next calculation is X transpose Y, which is going to be our X transpose here multiplied by our column vector Y, 75, 68, 55. And that works out to be 198 when we add the ones multiplied by the values. And then the second calculation works out to be 23,360 because we take the 100 times 75, 120 times 68, 140 times 55 and add all those up. Okay, now let's head into figuring out matrix A. So matrix A from our formula is going to be X transpose X inverse multiplied by X transpose Y. And so you can check the inverse calculation in Simpy. That works out to be, so I'm doing the inverse calculation of our X transpose X calculation from right here. Our 360 in the first row, 360, 44,000 in the second row. So this is 1 over 2,400, if you factor out the fraction part, times the 44,000. And you get negatives on these opposite diagonals. You can see since it was a 2 by 2 matrix, we're just able to use our inverse formula for 2 by 2 matrices. This is the determinant calculation, 1 over that diagonal multiplication and subtraction, and then the values flip from the diagonal in this diagonal, the values flip, and then the other values switch signs. And then we're going to multiply that by our X transpose Y calculation, the 198 over 23,360. And that gives us 1 over 2,400 multiplied by 302,400 and negative 1,200. So then if we simplify this by dividing each of these entries through by the 2,400, you get 126 and negative 0.5. So remember, these are our A naught, our constant in the linear equation, and our A1, our slope in the linear equation. So the line of best fit, or the least linear regression least squares line, is y equals negative 0.5x plus 126. So you would use this now to make predictions. We call it extrapolating statistics. So you might go back to our table and say, okay, what if X is, 130 of females in a tract? Or what if the percent is 40%? As long as you're using values that are relatively close, you can use our line of best fit here for predictions and extrapolations. So we'll see more of linear regression in chapter 5 as well. And if you take a statistics class, this is how we do many, many calculations in statistics.